Good evening, everyone. Thank you for coming. My normal audience is normally recovering from a night of drinking rather than doing the drinking. I think this is the first time the drinks are in people's hands rather than a memory of the night before. So let's see how this goes. So, as that introduction says, my name is Professor James Cheshire, and I'm really thrilled to be here this evening to talk to you about how we can map the invisible. And I want to share with you some of the examples of my visualizations, my cartography, using some of the new and interesting kinds of data that we now have. These are three of the books that I've co-authored with the designer Oliver Uberti. And so he and I are a geographer-designer team, and we're quite unique in the way that we work. So we work as equals in a partnership where I'm the academic doing a lot of the data processing. He does the design and helps and works out the storytelling and those other features. Normally, when an academic works with a designer, the academic creates a load of impenetrable graphs and visualizations that they then send to the poor designer, who then has to try and make them look good for the textbook or other publication that's being made. In our case, we work together at every single stage, and we think it makes a massive difference in the way that we can visualize the invisible. So the first question I think I need to answer is, what do we mean by invisible? And it can mean lots of different things. It can mean things that are too big and too distant to be seen easily by the naked eye, such as this image of the black hole that was created by the Event Horizon Telescope's team in 2020. And actually, it's an image that, of course, they're constantly refining. It can be things that are too small to be seen, such as this double helix in the DNA that was visualized first by Rosalind Franklin and Ray Gosling in 1952. It can be things that are deliberately hidden. In this case, this is the first map I'm going to show you this evening that Oliver and I created from a historic and classified database of US bombing missions in Cambodia during the Vietnam War. Now, to the Cambodians who had to live through the bombing and its consequences, which is still killing and injuring people to this day, as there's tremendous amounts of unexploded ordnance, of course, this was not an invisible phenomena. But to the American public, to the rest of the world, it was deliberately hidden until around the year 2000, when Bill Clinton declassified the maps that were created that detailed the targets and how many bombs were dropped on them, in order that the Cambodians could help pinpoint their efforts to parts of the country that were most intensively bombed, in the hope that they can find some of those unexploded bombs before they injure and kill more people. And this image is something that has a dual purpose. It shows us an important period of history that can actually be revealed just by looking at the data itself, the intensity of the bombs and when they fell. We can think of the invisible as things that are hidden in plain sight, such as inequalities in work. And so there's always an imbalance in gender roles, with women doing more unpaid work than men. And you'll be pleased to see that Denmark has men doing the longest hours of unpaid work, but there wasn't quite the parity that you get with Sweden, so they slightly edge it in the equality stakes. However, other countries, you just see the tip of the iceberg in the women's paid work, with much of their efforts hidden below the surface as unpaid, hidden labor, oftentimes just in the home. We can think of the invisible as things that have happened in the past that may have been lost to history until they've been digitized and until we can see the full scale of what was happening. Here's part of a map that we created that showed the extent of the US whaling fleet and industry between about 1760 and 1920. Whalers were meticulous log keepers because, of course, it was a business, it was a major industry. So they were creating logs of where their vessels were, whether they tried to capture a whale, whether they'd been successful or otherwise. And so here's just part of a map that shows the intensity of the whaling efforts in the Pacific region around Australia and New Zealand, and the routes taken by a couple of vessels as located in the logbooks that has since been digitized. And again, this is a data set that has a dual purpose. It was originally digitized by meteorologists who were interested in seeing what the weather conditions were like in the historic period, because in part of the ship's logs would contain weather data. But to ecologists, this is a historic record of where whales used to be found before they were eradicated from some parts of the ocean from this very industry. And so, again, it serves a dual purpose, and in a strange way, this map and maps like it have informed conservation efforts as people are looking to parts of the ocean where they knew whales used to be found, and whether their numbers are recovering there or not. And we might think of the invisible as things that are yet to happen, things that will impact us in the future. And so this is a map that shows the predicted increases in turbulence you're likely to experience if you take a flight, in this case, in around 2050. And the vomit-colored green gets more intense in the areas where there's highest increases in turbulence. And so it's pretty bad news if you're taking any flights in the Northern Hemisphere, particularly between the US and Europe. And of course, there's an irony here in that the very industry that is causing some of the changes in high-level turbulence due to climate change and global warming is also being made more uncomfortable for the passengers who are using it. And so we live in an era where there's lots of data. I'm going to talk a bit about that shortly. But I wanted just to take a moment to reflect on some of the pioneers of data visualization and mapping. These are people that lived in the 19th century, perhaps into the early 20th, who saw an opportunity for using maps and data graphics in a new way. And one of the kind of greatest pioneers, and I guess my hero in this, is someone called Heinrich Berghaus, and he worked with a very famous scientist, Alexander von Humboldt. And Humboldt wanted to visualize the cosmos. He was interested in how the world was interconnected, how a change in one thing could impact another. And he realized that to convey that complexity, you needed more than words. You needed maps and data visualizations. And so that's why he worked with Berghaus to create the first atlas of its kind. It was an atlas not about where things were, but it was about how things worked. And it was about climatic regions, the distributions of animals, the distributions of people, of geomagnetism, of temperature, of climate. And it's called the Physikalische Atlas, and it was first published in about 1848, and actually there were subsequent editions right up to the beginning of the 1900s. And it was really a basis for how you could visualize a complex world in a new way. And you have to remember, this stuff had never been visualized before. Like new diseases that were coming to kill and make people sick in this case, the British Isles. This is one of the first national maps of cholera to be made. It was made by a chap named August Petermann, who was actually Berghaus's adopted son. And in 1848, people were terrified about cholera. And if you got sick in Victorian Britain, it was because you lived an immoral life. That was the biggest reason, okay? You were someone that deserved to be sick. You were not someone that got sick for good reason. And so making this map and showing that the distribution of sickness was not random, it was in fact clustered in urban areas and rapidly urbanizing industrial areas. It was a revelation because it revealed that illness was not random. There may well have been something happening in these urban areas with very poor living conditions that could be explained and therefore could be prevented. Things like the weather was also an act of God. If it rained on you one day, that was something that wasn't to be predicted. It was something that just happened and you had to live with and endure. And so here's Joseph Henry updating one of the first weather maps. In the Smithsonian Institution in the 1840s and 50s, he benefited from the telegraph network that was newly installed, and it meant that people across North America could do their own weather measurements, telegraph them in, and then he was able to affix colored discs to his map that showed what the weather was like across America on any given day. And it didn't take long for people to realize that weather that was happening in a place today, perhaps to the east or to the west, would arrive tomorrow. And so that was a revelation that enabled the starting of weather forecasting and prediction. And again, it was something that was extremely controversial at the time because you were messing with God, effectively, to do that. If you wanted to explain something, you were trying to explain, the divine, and that was not something that was necessarily the done thing. So weather forecasting for 50 to 60 years after this point was an incredibly controversial science, as it remains to a certain extent today. If we think about trying to predict the impacts of climate change, there are still people that would rather deny what the science is telling them. There were new innovations too that were causing loads of additional data to be collected. The railways were invented, and so people had to buy tickets, and so you got an idea of how many people were traveling on certain lines by counting the tickets. And this is a page from a statistical atlas in 1890, published by the French Transport Ministry. It was an atlas they published almost every year for a couple of decades, showing how life in France was changing. It wasn't just transportation, but it was about cultural life as well, all collected by data. And you can imagine someone has had to count these tickets and then come up with a way of visualizing it. There were pioneers in trying to tackle some of the worst consequences of, in this case, of racism. And in the case of this particular map, it was created in 1921 by the Colored Women's Club of Michigan, who were trying to get through anti-lynching legislation. So it was an issue in the US where those who did not wish to bring forward legislation against lynching were saying it was a local issue, it was a local governance problem, not a national issue. And so pioneers like this group of women and many others created national maps to show that it was a national problem. And in this case, they are identifying in red key decision makers or policy makers who they thought they could swing in favor of the legislation. And it was a way of shaming politicians into action. Now, on the day of the vote, some of the congressmen fled the chamber, and they had to lock the doors to stop them from doing it. And even to this day, the US does not have any legislation that explicitly outlaws lynching. But this is an example of how maps were being discovered as a way of solving, or at least campaigning against, social problems. And so the pioneers of mapping had a lot of data by the standards of their contemporaries. But of course, this is nothing compared to what we have today. And this data that we have today is collected by all of us all the time, and it's stored on hard disks in the cloud, that we might, a phrase we might hear, and we never really get to see it. And so we can start to think about some of the data that's available. And you realize that the amount is truly extraordinary. What I'm showing you here is an ant's nest, and each colored dot is a QR code that the researchers have stuck to the back of every ant in the nest, and then they're using cameras to track the movement of the ants and give them these tails as they move and go about their business. And so if we can track every ant in a nest, what else are we doing? And why is it that data visualization is so powerful? Well, it's powerful because you can freeze time, and you can look at everything in one go and see what's happening. So you can process the behavioral data, and you can see that the ants have 3 key tasks. Some are nurses, tending to the brood. Some are cleaners, maintaining the nest. And then others are foragers, who obviously leave the nest in search of food. And you can see they stick to certain parts of the nest. You can also look at the data and reveal that the ants change jobs throughout their life as their interactions vary and as they age. They start off as nurses doing the babysitting, they graduate on to becoming cleaners, and then they finish their life as foragers. And so it's an enormous complexity of data that you can actually distill down into a single image. Now, of course, if we're tracking ants, as I said, what else are we doing? Well, we actually often track ourselves in unprecedented detail. This is a map from 2013, so it's something that's been happening for a while. It's created from data using the fitness app Strava, which at the time was actually quite a new app. And it shows the journeys of cyclists in London around rush hour. And it was one of the first images that we created of London that was showing flows of cyclists in a way that wasn't just simply by someone standing on a street and counting bikes as they go by. Now, London isn't a city you think of as a big cycling city, but actually there are lots of cyclists, and it's a thing that's increasing all the time. And so you can use a map like this to look at preferred routes and to understand where provision perhaps is lacking or could be improved. And it's that technology, it's that GPS in your phone, it's that connection to a database that has made such a huge difference. One of my favorite examples of another big change comes from this map we created of snowy owls in North America. These owls were equipped with the same technology as the cyclists on Strava, but it was slightly smaller, and from it you could track where the owls were going, and they were found much further south than is usual for the species. And what the researchers discovered was that the owls were spending a long time over some of the Great Lakes, and this was slightly strange because you would expect an owl to spend its time in fields hunting for mice and voles and that kind of thing. And they discovered that certain owls, this one's called Erie, were spending time hunting waterfowl over the lakes. And why I think this is such a great example of another change is because it demonstrates that you can actually add contextual data to what's being collected. And in this case, the context we're providing is a satellite image taken about the time that the owls were spending over the lake. And so we can now add satellite imagery to give us that important background, to tell us what's going on. If we just used a standard Google map here, or any kind of satellite image, it would make no sense at all, because you would not see the particular pieces of ice that the owls were spending their time on. This makes perfect sense, and it is something that we can do all the time now from satellite imagery. We're allowed to track things and add that important context. One of my other favorite examples of this was how we finish the book, Atlas of the Invisible. And it shows the tracks of historic icebergs that have been followed by satellite imagery. And in particular, this big iceberg, one of the largest ever recorded, breaking off from the Larsen ice shelf and kind of spiraling towards South Georgia, where it hits shallower seas and it breaks up. And it's an example of how we can go one step further with satellite imagery. We've got the imagery, and now, actually, we can process it in a way that allows us to track things. So the big iceberg was actually tracked by individual researchers, but there's lots of other tracks on there that were just created by algorithms that detected, that kind of recognized what an iceberg looked like and could follow it. And so we can apply that technology in other ways to monitor the health of our oceans, for example. And so this is the Pacific Ocean. We've got China, North America, South America, Antarctica, and Australia around the edge, so it's a slightly different view of the ocean here. And the red colors show the intensity of the fishing that's taking place in that ocean. And that's created both by satellite monitoring, but also from the vessel signals that are sent out. But the satellite imagery and this vessel tracking can be combined with algorithms to detect unusual behaviors. For example, if a fishing boat is fishing in a part of the ocean that it shouldn't be in. And so you can actually begin to monitor illegal fishing and illegal catches. And Global Fishing Watch, who's the organization that do much of this work collecting the data, they're also looking at things about illegal transfers and shipments of fish in the ocean to avoid some of the legal implications of what they're doing. So again, it's another example of where we can just be tracking the world, and a single visualization can then give us that snapshot in time of what it reveals. So how do we do this? How do we visualize the invisible? And so this process is really important because it's something that I think scientists, as I mentioned at the beginning of the talk, often overlook because they're so busy finishing what they want to do, the experiment or whatever, stick the graph in their paper or chapter, and then ship it off, hopefully never to look at again, because it was never something that perhaps they enjoyed doing, or they were so tired of and so relieved to get it through peer review and all that kind of stuff. I know the feeling, but being able to tell a compelling story and think about what the data reveals actually adds so much more power to the work. And there are certain things that we need to think about. And actually, there are 4 things that Oliver and I think about all the time. We think about the topic we're interested in. We're thinking about the data available to tackle that particular topic. We then think about the angle we might take. What's the story we're trying to tell with this data? And then we think about the final thing, which is the form. How is the graphic going to look in the end? And there are certain things that we might need to do, and specifically things that I work on, in order to fit this kind of topic, data, angle, form mantra that we have. And in some cases, we think about simplifying the data, generalizing it, or in technical speak, aggregating the data. And we do that by perhaps assigning individual data points to particular grid cells. In this case, this is data that shows mobile phone activity in Washington, and actually in a specific area around DuPont Circle in Washington, where yellow shows higher areas of activity, blue lower. And the way that the data come in is as a series of points, which effectively are the locations or the approximate locations of phones. And so in order to visualize it, we can't put all of those on the page in a single way. So we might assign them to individual cells. And so we might count cells in a small square to see and give us a count on that. Or we might actually create slightly larger squares and give us a count on that. Each one of these stages looks slightly differently, but actually we can pick the best one for the page, for the layout, and we can decide what works best. Now, this map was actually created pretty early on, actually, during the onset of COVID-19. And many of these data sets, looking at mobile phone data and where people were moving and so on, work was underway, but it took this huge new significance when we were interested in how people were mixing in order to see how a disease would spread between them. And actually knowing how many people are in an area can be really important too. So this work, this combining points and aggregating it up as we do, is something that's happening all the time now, kind of behind the scenes with mobile phone data. I mentioned before just now that we're interested in taking data and perhaps pulling it out of scientific publications and bringing it to places like, concert halls in Copenhagen in such a way that people find a bit more interesting and a bit more engaging. And so this is an image that was taken from a scientific publication, and it shows the speed of ice on the Greenland ice cap. And that speed has been calculated by some of this satellite technology I've already been talking about, where you can take multiple images across the ice cap, and you can compare them, and there's other sensors too that you can bring in, and those comparisons enable you to see how the ice is moving. But it looks kind of static. You can see fast and slow, but it's actually hard to kind of discern that this is about ice, this is ice movements. And so Oliver and I can start to think about how do we layer different levels of data together in order to create that more compelling image. And so in this case, we've got 3 different layers that we're showing. The first is just the rocks, and so we're thinking about how do we show the cliff faces, the peaks, the valleys, and so on, that are not covered in snow and ice. You can then take another image and process it to make it look like this pillow of ice that sits on the top, and so that's a data set. And then the final stage was, I kind of did a thing where you take, if you imagine taking about 100,000 tennis balls and throwing them on the ice surface, and then just like I showed with the ants, showing how those tennis balls are moving with the ice and drawing a tail on them, that gives you the image we see on the right-hand side there. So we're creating these points that I'm moving according to the data that that's shown in the academic paper to generate these tails that we can then color according to the speed that those particular points are moving. And you create this final image like this. And so you can see straight away we're dealing with flows. We're dealing with things that are moving at different speeds, with slow ice at the peak of the ice cap and then accelerating ice towards the edges. And it helps bring it alive. It gives it dynamism, and it helps it relate to some of the other topics that we're trying to cover here, related to how warming ice creates further problems. It creates accelerating ice, which creates more warming ice, which creates more melting, more sea level rise. But sometimes you get data, and it looks like this, a complete mess. And so you have to put a lot of effort in to cleaning it up in such a way that it's compelling and interesting for the reader. And so this is a global flights data set. The way that it's collected is people have volunteers have boxes that detect the signals of the planes going over. And so if you have an array of these boxes that are detecting the plane signals, you can get a sense of how many planes are overhead, and you can chain the plane together as it passes over multiple boxes. But of course, if there aren't any volunteers with boxes, then you don't get any data. And so nothing comes back over oceans. We can see Africa is missing here if you just squint. There's no Africa, not much in South America. There's a bit of Asia, but it's a mess. If you zoom in, it looks even worse. I've colored this by the elevation that the plane is at. So blue is closer to the ground, yellow is higher. And so you can see that there's some structure poking through. We've got airports, by the looks of things, coming through as planes come into land in those blues. But it's still not good enough. And so I had to write some computer scripts that followed every plane along the line and said, well, if the plane has stopped and then we don't have any information about that flight for a long distance, we haven't got any data there, so we'll break that line. We look for duplicates in the data set and we remove those. We look for planes that are going at 10,000 miles an hour and all kinds of other crazy things that happen in the data. And after a lot of computation, you get something that looks a bit like this, which is much clearer already. So this time yellow is the lower planes, red is still the higher ones. But we can see what's missing from the map and what we have quite clearly. So that's, the topic is flights, the data we now have, and now we need to think about the angle that we're going to apply. And so this is where working with Oliver as a designer makes such a difference, because we can stick drafts of our data on a page to see how they appear in the book, and we can begin to ask ourselves, well, what is this showing? What's the story we're trying to tell? And the key takeaway for me on this graphic was just how busy the skies are over Europe. And this is a week of flights, and it was thousands and thousands and thousands and thousands of flights showing this interconnected network. We actually found the different colors a bit distracting. We thought, well, that's not helping tell the story. And so I stripped it back, and we just looked at them as black and white lines, adjusting the line thickness and the transparency and all kinds of things. And straight away, there's clarity there that I think the previous image didn't have. And so for the final graphic, it all came together because we're interested in carbon overhead, what the impacts of these flights were on these busy skies. And so you could create an image that looked like carbon pencil had been just scratched over paper to create the kind of chaotic and yet beautiful image of our busy skies. A map that was created before global travel kind of ceased and slowed down prior to the COVID-19 pandemic, and a map that we might ask ourselves if it's something we want to return to in the future. So just to kind of finish up for the last few slides, I wanted to talk about the power of maps, the things that maps can do that perhaps other things are less good at. So the first example is one where a map has shown something it probably shouldn't have done. And so I was talking at the beginning about the Strava data set. And Strava as a company, as I say, the map was created about 2013. It has since become extremely popular. And for these maps, they emerged when Strava published a global version of the map of London I showed you that showed all the global activities. Except what they didn't realize was that the US military had issued its personnel with fitness watches, and many of those personnel signed up for Strava, didn't read the data sharing agreement, and you created a map of US military bases. And so this was the Bagram Air Base on the left-hand side. You can see. On the right-hand side, I honestly can't remember where I took this screenshot from, and it may be just as well. But this is another military base in the middle of no other Strava data. You just get this hotspot on the map, and you can zoom in, and you can actually see, I think that's helicopters or flights taking off with the watches still activated. So the US military for this had effectively doxed themselves, and there was a tremendous outcry blaming Strava, but Strava just held their hands up and said, well, we didn't realize you guys would have done that, and we just put out there what we have. But it's a great example of how data can sometimes reveal more than we want it to. But maps and data can be an incredibly compelling argument for doing things better and more efficiently. And this is one of the strongest, I think, that we include in the book that we've just published. It's from Flint, and so many of you will be aware that Flint in Michigan has been afflicted by water poisoning because lead has been leaching out of the pipes into their water supply due to a change in the source of their water. And this has caused all kinds of horrific kind of health implications for the people that live there. So to solve the problem, they had to go in and dig up the pipes that contained lead. And researchers at the University of Michigan, they created a model or a map that showed where they thought the highest risk of lead would be. And in so doing, they could target the intervention. And the city got a 70% hit rate. So every time it dug a hole, 70% of the time it dug a hole, it found a lead pipe and was able to solve that problem. The problem was, with this approach, that it wasn't necessarily politically the most expedient option for them, because more affluent areas towards the edges were unaffected by the lead poisoning, but they wanted their pipes dug up and checked as well. And so the city threw out the map and said, right, we're just going to do digging in some of these outer areas. Their hit rate dropped to 15%. So only 15% of the holes that they were digging, they were finding lead pipes, an enormous waste of resource. And so finally they conceded in March 2019 and went back to this model, and the hit rate went back up to 58%. And so it's a brilliant example of how, there's truth in the data that may not be a convenient truth for some of the people in power, but actually it's one that matters if it comes to dealing with people's health. Thinking too about health, we can reveal things that are invisible to us, but actually quite lethal. This is a map of nitrogen dioxide created by the Copernicus satellite. Its image, it generates this map every single day that shows us where the nitrogen dioxide levels are. And this is a hot day in July 2019. And right away, you can see the impacts of geography. You can see how, to the north of Italy, the Alps are creating a barrier that the nitrogen dioxide is pooling under. You can see how the cruise industry and shipping has caused a peak in nitrogen dioxide around Marseille. And you can see how the Rhine industrial area, along with the channel and the flights over the channel and everything else I've shown, is creating kind of a swirl of nitrogen dioxide that sits over the United Kingdom. And so just as we start to think about forecasting weather, we can also think about forecasting pollution in much more detail, and some weather apps now have this in order that people who have particular health concerns can plan appropriately for it. Maps also tell us an unequivocal truth about some of the real consequences of geopolitics. And so blue on this map are parts of Syria, particularly, where there has been a dimming of the night lights. So urban areas, a satellite can look at how much light emissions there are, and if there's a dimming, we've colored it blue. If lights have got brighter, we color it yellow. And straight away, you can see the impacts of the Syrian war on the night lights of that country. But then around the edge, you have this halo of yellow, which in some cases, in quite a number of cases, in fact, are new settlements, refugee camps appearing where the displaced people have had to move over the border to safety, and they're now creating their own lights in areas that were previously uninhabited. We can use maps to reflect on who we are and what makes us happy and what's important. And so this is a map showing life satisfaction and personal well-being around the world. And we've colored the faces, we've sized the faces according to the GDP per capita, so how wealthy the individuals are. And you can start to ask yourself, are people with more money happier? The answer is not always yes for that. And so there are some interesting patterns and exceptions both in either direction. And we can start to look at the interactions of different features of different cultures, economies, so on and so forth. We can offer fresh perspectives on the world, and so this is a different kind of projection called the Spillhouse projection, which shows the ocean as a single entity. I would quite like a swimming pool shaped like this, but may not be something I can do straight away. But still, it gives you the impression that it demonstrates that the Earth is this single body of water, and so the impacts in one ocean can impact on the ocean currents and the cyclones and so on that happen in another. A different perspective, making people think twice about what they see on the map. And we can locate ourselves in space and time by using maps. And so this is our take on the climate stripes graphic that many of you may have seen that go from blue to red. It was created by Ed Hawkins, and you'll see it a lot now during COP26. But we've added maps in every single one of those tiles, and it's tricky to see for some of you, I'm sure, but it enables you to look really carefully, and you can see the temperatures go from 1890 at the top on the left to 1899 at the bottom on the left, and then every decade since until 2000 to 2019. And the big story here is both the fact that the overall picture is a warming one, but it also shows that parts of the world used to have heat waves. We used to have warming events in other specific locations in the 40s and the 50s and the 60s. But those events were exceptional to the planet as a whole. And now, if you look at the 10 warmest years on record, most of them happened in the last decade or so. And so the hot spots are overlain on a general warming pattern across the Earth, not just these specific one-off events. And so we can locate ourselves here. So I'd like to thank you for your attention this evening and for coming. And I would like to leave you with the thought that I think maps are some of the most powerful tools we have for navigating a potentially very uncertain future. It's not about seeing maps as things we can look at on our phone just to navigate where we want to get to, a particular street, or even just to see where a particular country is relative to other countries. Maps are brilliant at showing complex things in a compelling and engaging way. And so using maps to reveal the hidden patterns that are in the billions and billions of data points that tell us about our planet and ourselves are really something that we should be doing much more of. And hopefully, I've inspired one or two of you this evening to take up the cause. Thank you very much.